Okay, so just going to point a couple of things out. On the Canvas page, under the in-class data folder, I put a folder called linear regression files. So we'll work with a couple of these today. But this will basically be what we're going to be using the rest of this week and next week to kind of look at some linear regression stuff. I also, since last class, posted the 5th Connect assignment. I'll put up the 5th Excel assignment after class today as well. So remember, this was the idea that these 5th assignments, if you've already done the first 4, I dropped the lowest one, right? So, if you're, feel pretty confident with those first 4 Connect or those first 4 Excel, and you don't do the 5th one, well, that's going to be a 0 and that'll get dropped, right? So this is where kind of front loading your effort in the course always kind of makes the end easier, but I'll get that 5th Excel up today after we kind of see just a little bit of the work that we can do for linear regression. So we left off talking about matched pairs. So we'll pick up kind of with this hypothesis test of different statistics, right? So we've been doing hypothesis testing, kind of comparing two populations, been able to say, does this group have a higher mean than the other? But we, going back, we might also want to look at the relationship between two variables, right? So if we go back far enough, we talked about things like the correlation coefficient and the covariance. We said, if these are positive, that means that as x goes up, y tends to go up as well. If it's negative, as x goes up, y tends to go down. And if it's 0, as x goes up, y tends just to not change. But we can actually get a better measure of what the true relationship is between two variables by doing something called linear regression, okay? So, we're thinking about what we really ultimately want to know is as x goes up, what does y tend to do? Does it go up, does it go down, or does it stay the same? So for any two variables we can think of, and I'll come back to here in a second, but I want to try to get a good setup of this so we get a good understanding going into this last kind of topic. There we go. So, if we think about any two variables, x and y, right? Maybe this is something like, I don't know, the x variable here is the years of education and y is income, if we want to have something to kind of, some actual names to give to them. Why isn't this fitting all in one line? Okay. So let's say I had this data set and it's got, a bunch of different individuals, the number of years of education, their income. So maybe the first person has, I don't know, this many years of education, and there's their income. This person, here's their education, here's their income. I basically would have every single data point would be, right? I could kind of create this scatter plot, right? So every observation, I'm just plotting that, okay? Once I have this data kind of in a scatter plot, the nice visual here, what I could do is try to find a line that best fits that data, right? So you might have heard of this, in previous classes. I think like in the sciences, they do this even in high school, where you've got this data and you're, okay, where would this line that kind of best fits this data, right? Or kind of the relationship between this x and y variable. Well, that line is going to have some intercept and, right, some slope, okay? So, I could think about really here, I could say, well, income is going to start at this intercept, and then as x goes up, as the number of years of education goes up, then the predicted y value also goes up, right? Or I'm kind of adding b to that intercept for every additional year of education. So that's the ultimate goal of what we're going to try to do with linear regression is we have two variables. We know that there's some relationship that exists. This data is just sample data, so it's kind of just a, sample evidence. But if we could get a line of best fit through this data, whatever the values for A and B would be that give us that line of best fit, that's going to allow us to then make predictions about somebody's income given their years of education, or make predictions about our Y variable given different values of our X variable, okay? That's ultimately what we're going to try to do. Okay? So I think I'm going to jump the gun here a little bit, but I think it's, I don't know, I think I'm going to try explaining it this way instead of kind of how it's up in the slide. So we have this line of best fit, right? We don't have to worry about how I'm doing it yet, but somehow I'm able to choose an A and B value such that if I then draw out this predicted income line, right, I would have a line that best fits this data. Well, if I do that, right, I'm going to have some issues because think about for this observation. So let's say this person has, I don't know, 10 years of education. We plug a 10 in here, whatever the A and B values were that gave us that line of best fit. But once I have those A and B values, I can plug 10 in and get my predicted income, right? So this predicted income at this X value, I can think about this is, we're going to call that Y hat, right? If I plug in some X value, I can get the predicted Y. That's just the point that's on that line. However, the actual observation here, the actual Y value, I can almost think about it as, here's my actual Y value. There's going to be a difference between the two, okay? So that difference is what we're going to call epsilon, or this error term, right? It's how far off my prediction was, okay? In this case, my prediction was too high, right? But we're actually going to look at the difference between the actual Y and the predicted Y. So when we talk about this error term, it's going to be the difference between the actual Y and the predicted Y. Well, here, if my predicted Y is too large, then my error term would be negative, right? The predicted value is larger than the actual value. Maybe I, plug in, where can I get a good one here? Looks like right here. So let's say, I don't know, plug in this X value. Here's my kind of predicted Y. Here's the actual Y, right? So I could think about, if I was trying to, well, these aren't going to be perfectly straight, but here's my new predicted Y value. Here's my actual Y. In this case, this epsilon term, well, the predicted Y is actually lower than the actual Y, so I'd have kind of a positive error, right? It's not positive in the sense that it's good. It's just that the value of how far off I was positive. So I could think about this exists for every single observation, right? For every single observation, I could take that X value, tell you what the predicted income should be, but it's going to be a little bit off, right? Because education isn't the only thing that matters in predicting income. I'm leaving a lot of things out of the story. So for any one individual, I can probably get a pretty close predicted income, but there's other factors that I'm not accounting for so that their actual income is actually going to be a little bit different. And that would exist for every single observation here, right? I'd have an error term for every single observation. Okay? So that's kind of a broad overview of what we're doing. We'll kind of break it down a little bit more. I'll probably reiterate some of those things. I'll wait for the screen to catch up in class here. Oh, hopefully it catches up. Okay. So we're going to have this line, and what we're ultimately going to try to do is estimate what those A and B values should be, okay? So some terms that I'll start using, when we're thinking about this Y variable, we're going to call this the dependent variable. So Y variable, dependent variable, or that left-hand side variable, right? If we think about it, my Y variable depends on this X variable, right? I'm predicting this Y variable given different values for the X variable. That X variable we're going to call the independent variable, right? It's what is changing on its own and then causing changes to our Y variable. So dependent left-hand side Y variable, independent right-hand side X variable. Right? Kind of those are all kind of interchangeable terms there. So what we're going to do is use this regression analysis technique to come up with an estimate for what the relationship is between this dependent and independent variable. Okay. Now, when we come up with this estimate, right, it's I kind of already described this, but we're really just trying to get a line that best fits the data, right? That's all we're trying to do. Once we get the line that best fits the data, well, now if I have A and B values, I can then predict Y for any given value of X. I've kind of already went over this and drawing this out. You can kind of imagine, right, if I had something that looked like this, what would that value for B be, right? If I'm thinking about I have this value B that tells me the relationship between X and Y. In this situation, the value of B would be not a specific number, but I know that it's going to be, it's a downward sloping line, then B would be negative, right? I'd have a negative kind of slope here. If I have a flat line, my value for that slope would be 0, right? If I have a positive linear relationship, the sign of that slope B is positive, right? If I have a kind of upward sloping kind of best line of best fit here. So we're going to try to get, estimate, to see which of these are the scenarios that we have, right? Do we have kind of this inverse relationship where as X goes up, Y tends to be lower? Do I have no relationship where as X goes up, Y just kind of does its own thing? Or as X goes up, do I see that Y tends to be higher as well? Right? That's what we're going to try to estimate. Now we can do things with nonlinear relationships. It's kind of outside the scope of this class, so we won't actually go over this. Maybe at the end of next week, I'll show you what this looks like, but not, have anything like this on the exam. But we can do things that aren't linear relationships as well. But for the sake of this class, we'll keep it easy. We'll just do linear relationships. Okay? But you can imagine there might exist relationships that look like this as well. So what we're going to try to do, right? The actual Y value would be whatever we predict, and then plus this error term, right? So if I think about what I was doing here, right, the actual Y value is the predicted Y, and then add in that negative error term here, right? For every single observation, they're going to have their own error term. Okay? So what we want to do, is we can think about, we also have the predicted Y value. The predicted Y is basically just the same as Y, just without the error term. So if I'm thinking about the actual Y, it's just the predicted Y plus that error term, right? It's kind of different ways of looking at this. But we already, already kind of mentioned this. So I gave you a nice visual here in the slides, but I also did this by hand, right? We can think about the actual Y and the predicted Y aren't going to be exactly the same. Notice for this observation, we're making a pretty big error. But then for some other observations, right, the error isn't as large. In fact, some of them, like this one here, the predicted Y is almost exactly equal to the actual Y. So for this, my mouse went away. For this observation, our error term would be almost 0, right? Because that observation almost falls exactly on my line of best fit. And my mouse went away again, this guy right here, okay? So we've got all these errors. Like every observation, we're making some kind of an error. So what we're going to do is how do I find that A and B value? So this is where I'm going to punt a lot on the math and we're going to kind of gloss over that and get to just the interpretation. Okay. So what we would really want to do if we're trying to choose the line of best fit, the values A and B that would give us that line of best fit, is we want to minimize all those errors we're making, right? So all these errors we're making, we want to get a line such that the errors, or if we added up all the errors, we're minimizing that. Right now, clearly, like if I have a line of best fit and I draw it way up here, well, I have huge error terms to all of my observations, right? This is very clearly visually not the line of best fit, right? So I'm trying to choose the line such that when I add up all these errors, I've minimized those errors, right? I think that's kind of intuitive, right? I'm trying to draw a line such that the errors I'm making are as small as possible. Now, we don't just minimize the sum of the errors, we minimize the sum of the squared error terms. One thing, one reason we might want to do that is, well, first of all, positive and negative errors, we don't care which direction we're off, we just care that we're making the error. So by squaring it, negative and positive errors both become positive. And then squaring the errors also is really going to, similar to when we were calculating, hold on, there we go. Similar to when we were calculating the variance, we said if we had a really extreme error, right, like our prediction is way off, well, when we square this, 1 squared is 1, 2 squared is 4, right? So by squaring it, we're really penalizing large errors, right? We don't want to be making really bad predictions. So we're going to kind of over penalize ourselves when we add up the sum of the squared error terms, okay? So that's essentially how we're going to choose A and B, because if I write this equation out, right, I'm trying to minimize the sum of my squared errors. And the error is just the difference between the Y and the predicted Y, actual Y and predicted Y. I could then plug in the equation that I know, gives me that predicted Y value. I'm trying to choose A and B, so I would take a derivative of this function in respect to A, a derivative in respect to B, whoops, and then set those equal to 0. I have two equations, two unknowns. I could then solve this, all right? Now, you don't have to know how to take the derivative of this function. You don't have to solve these equations every time, because with a simple linear regression, oops, I don't know why I put that slide in there again. So in a simple linear regression, once you take those derivatives, set the equations equal to 0, two equations, two unknowns, you can actually solve for what the A and B value would be that would best fit that data. That would minimize the sum of those squared error terms. Okay? So you don't have to, like I said, you don't have to understand that, like all the calculus behind that. It's just that if we were to do it, it's always going to work out to be like these two equations. Okay? Now, you can kind of imagine I could probably do this in Excel if I had the data, right? I could calculate the average X value, the average Y value, then in a separate column for every observation, take the X value and subtract the mean, multiply that by the Y value minus the mean. You then add them all up, you get your numerator. Like, you could do this in Excel step by step, and I don't think I'll get there today, but maybe on Friday I'll show you what this would look like in Excel. But there's a much easier way to do that where Excel is going to do this behind the scenes for us. Okay? So there's another, if we're doing this by hand, here's another kind of, if we could rewrite this. This doesn't matter. I'm not going to make you use these equations. Okay? Because I'd rather have you understand the application and interpretation of what we can do with linear regression. Okay? So you're not going to have to worry about these equations or kind of use these. Okay? So I'm going to skip through this and then go to show you there's a way to do this in Excel. All right, so, oh, that's not what I wanted to do. Sorry, hit escape. There we go. So I'm going to start with this GPA data. All right, so this is up there on Canvas under that linear regression folder that's in the in-class data folder. All right, that GPA data. Okay. So we've got a bunch of different individuals. In college, we've got what their GPA is, what their SAT score was, a bunch of other information. Okay? So what I'm thinking about here is that I want to try to predict what somebody's GPA would be, right? Maybe I'm like in college admissions or something. So I'm thinking that I can come up with predictions for somebody's GPA based off what their SAT score was. Okay? So if I can get these estimates for what A and B are from Excel, right, using this linear regression, I show you the formulas that you could, calculate it by hand. It's going to be a pain if we did that. But once I get these estimates for what the intercept and what the slope coefficient, and I'll use this term coefficient, it's kind of what we reference the slope as, but it's a slope coefficient, it's a slope, there's different ways of saying the same thing. Once I can obtain these values, I can come up with predictions for what someone's GPA would be just based off of plugging in what their SAT score was. Okay? So how am I going to do this? I will show you. So in Excel, first thing we're going to have to do, and it's a little bit different on a Mac. I think you go underneath the Tools tab on a Mac. However, you would get to Options, right? So if I go File, on a PC, it's just File and then Options. I think, like I said, in a Mac, it might be like a different tab up here, or you can go directly to, there's like a Tools, and then when you pull up from the Tools, you'll see this Add-ins option, okay? But for regular PC, File, Options. So then we go to Add-ins, maybe, there we go. We see all these different add-ins. I'm going to go down here to manage them, right? Once again, I think on some of the newer Macs, once you get to the add-ins, it might just pop up with what I'm about to show you, which is these different options. Okay. So once we manage the add-ins, make sure that analysis tool pack has a check mark next to it. Now when I go to my data tab, I'll see this data analysis option over on the right-hand side. Okay. So like I said, I don't have a Mac to walk through those steps with you. I'll try to get a detail, like a kind of a photo screenshot of how you would do this in a Mac and get that posted up on Canvas if you need some help with that. But like I said, if I remember right, a lot of times the add-ins are under Tools on a Mac. If you're unable to kind of get it in, if you have an older one, I know there's also sometimes some things you have to download. So please reach out. That fifth Excel assignment I'm going to post, I'm going to have you do exactly what I'm doing right here. So you need to have this data analysis option in there. So I'm going to click on that data analysis. I'm going to go down here, select regression. Hit OK. Now it's going to ask me what my Y and X variable are. Well, if I remember, my Y variable is GPA, my X variable was the SAT score, right? So my Y variable, I'm going to go over and select GPA. So I'm going to select the label, hold Control Shift and hit the down arrow or Command Shift on a Mac. It's going to select that entire column of data for me. And then I go select my X variable. Oh, usually it sends me back up to the top. I guess I have to scroll up here. I'm just going to include SAT score. I'm just going to look at this SAT score variable. Control Shift or Command Shift on the Mac, hit the down arrow. I selected the labels, right? I selected those kind of titles of what the variables were. And you can put this on the same sheet by selecting like the output range, or just put it on a new worksheet. New worksheet should be the default. You don't have to click any of this other stuff. Don't click constant is 0. You just want to say that you selected the labels. Now if I hit OK, it's going to work for a little bit. And basically what it did was it took the data and it did all of this work, right? It took the difference between the, it calculated the average X, average GPA, average SAT score. And for every observation, took the difference between those, multiplied them, and then added them. Like it did all that for you behind the scenes, and then spit out at you what that A and B value would be. And that is seen in this first column down here, which we call these coefficients, right? So here's my intercept coefficient. Here's my slope coefficient on that SAT score variable. Okay. Any questions up to this point? Okay. So what this slope coefficient is the predicted value of what the actual slope is, right? There's an actual relationship between the SAT score and the GPA. I only have sample data. So it goes back to really what we're doing is we're getting an estimate for what that slope is. And we call that estimate the coefficient. Okay. So what I know is true as long as I have a sample size over 30, right? That central limit theorem is met. My slope coefficient should be centered around whatever that true slope value is, right? Whatever the true slope or the true relationship between SAT scores and GPA would be. Now, we usually have a standard deviation here. What we're going to call this now is kind of, usually it's written like this, the standard error term, or S kind of epsilon, right? But it really, an easier way to think about this is the standard error really is kind of like a standard deviation on that sample statistic, or the standard deviation on that slope coefficient. That might be another way you can think about it. We can kind of already imagine I could do things like find test statistics, right? Because my test statistic should just be whatever the sample statistic I found was, subtract the assumed true value of the population, and here we're going to want to divide by this standard deviation of our sample statistic that we're looking at, which here I said we can just reference as the standard error. It's the same procedure as what we were doing before. It's actually that it just becomes a little bit easier because Excel is going to give us this slope coefficient. It's going to give us the standard error, and we're always going to use an assumed true slope of 0. So really the test statistic just becomes take that coefficient estimate that Excel tells you, divide it by the standard error, and that's your test statistic. You could then look that up in a student t-distribution and find the p-value, but you don't have to because Excel is going to give that to you. Okay? So notice Excel gives us that test statistic. How did it find that test statistic? It was simply the coefficient divided by, in this column, it's our standard error. That's how we're getting our test statistics, right? Here we can see the full words here. Now it also gives us our p-value, right? And we make the rejection decisions the same way that we always have been. So what we're going to start out with for every single regression, we assume that these slope coefficients are 0. So every single regression, we're going to assume these slope coefficients are equal to 0 because we're trying to find if they're not, right? Or they're not equal to 0. So anytime I have a p-value that's less than alpha, same kind of thing as before, I reject, right? So if I find a slope coefficient and it has a p-value that's less than alpha, then I can reject with that level of significance, right? What am I rejecting? I'm rejecting that there's no relationship between that x and y variable. So if I go ahead and look at this output, 2e to the negative 166 means move the decimal 166 spots to the left, right? This is basically 0. So with a p-value of 0, I can say, right, 0 is less than an alpha of 0.1. So with 1% significance, there is a relationship. You know, I can reject that there's no relationship, or that I found strong evidence that there is a relationship between SAT scores and college GPAs. Okay? Any questions or anything kind of there? So it's, you know, we've got a similar step to what we were doing before in the sense that we do have this null hypothesis. Okay. Seemed like a bit much. We do have this null hypothesis always in the background, which is that we assume there's no relationship, or that that slope is equal to 0. If we can find a p-value that's less than, you know, whatever alpha we want to look at, you know, could be the 10, 5, or 1% significance level, well, then we can reject this, right? We found strong evidence that there is a relationship between our x and y variable. Okay. Yeah. Any questions on that? Okay. So the next thing that we're going to want to do is start to think about how we interpret these slope values. Okay. So for this SAT coefficient, the general interpretation of a slope coefficient is the following. A 1 unit increase in x causes the predicted y value to either increase or decrease by whatever that coefficient value is. Okay? So a 1 unit change in our x variable here would be 1 more point on the SAT, predicts a college GPA that would be 0.0019 higher, right? Or a 0.0019 increase in the predicted college GPA. So it's just a 1 unit, which in this case would be 1 more point, right? That's the units. And then our predicted Y, our predicted GPA would, and I guess I could say here, predicts a college GPA, if you wanted to, increase of 0.0019, just so we can kind of keep that language more consistent. Okay? But really, I'm saying the same thing there. I'm just trying to make it a little bit easier to line it up with that kind of general interpretation. Okay? Well, if this is the impact of 1 point, right, this seems really small. But 1 point on the SAT, right, someone with a 1200 versus a 1201, yeah, I don't think that the predicted GPA of the person with a 1201 should be that much higher, right? It's pretty much the same person. But if I think about, well, what's the, here, let's say, what's the impact of 100 points higher? Right? Well, if I know the impact of 1 more point on the predicted GPA, the impact of 100 points would just be the effect of 1 point times 100. Right? So if I get 100 points higher on the SAT, I would predict that the college GPA would be about 0.19 higher, which doesn't seem like a lot, but right, it's only between 0 and 4, right? We don't have a lot of room to kind of move up. You can think about 200 points. You just take that effect of 1 point and multiply by 200, right? You kind of come up with all these different interpretations, but it all starts with the coefficient interpretation is 1 more point in the SAT would predict that GPA is increased by that 0.0019. Okay. Any questions over that? And we'll be going through more examples and getting more interpretation, but this is kind of our general interpretation. So that was for our slope coefficient. What about for the intercept? All right. So the way we interpret the intercept is a little weird. And once we kind of keep moving through stuff, we'll see that it gets even weirder. But the idea of the intercept is, and I'll type it out first and then kind of give you a justification. So the predicted y value when the x variable is equal to 0, right? So here, the predicted GPA for someone with a 0 SAT score would be 0.66, right? Or 0.663. Okay. So it's the predicted y value when the x variable is equal to 0. Now, obviously, it doesn't make a lot of sense that we would have someone with a 0 SAT score, right? But that's still how we interpret the intercept. Okay. So it may not be like real applicable, but this is how we interpret it. Okay. And the reason why is because that's literally what it is. If we think about having, well, actually we could do this one. If we think about trying to come up with predictions for what the GPA is, the intercept is the predicted GPA when our x variable is equal to 0. Because when this is equal to 0, this goes away, and our predicted GPA is just the intercept. So that's why it is the interpretation that it is. And we can end up with some weird scenarios. Like that one, it didn't happen to be like this, but it very well could have. Let's say we had, I don't know, SAT and GPA. And let's say the data looks something like this. I don't know. Got a bunch of data over here. Well, if I try to draw this line of best fit, notice that is a pretty good line of best fit, but I'm going to have a negative intercept. Well, when I go to interpret the intercept, it's going to be, okay, when someone gets a 0 on the SAT score, their predicted GPA is negative something. How can you get a negative GPA? Well, that interpretation seems weird, and that's only because we just don't see any data points kind of below, like whatever this SAT score is, right? As long as you just show up and take it, you're not going to get a 0. So sometimes we get these weird interpretations of the intercept that just aren't like realistic, but that's okay, right? That still is going to give us this line of best fit. And in application, it doesn't matter. We're never going to get negative predicted GPA values because no one actually scores that low on the SAT score. So just kind of pointing that out. Sometimes the intercept will have a weird interpretation for the example that you're looking at. Okay. All right, any other questions on that? Otherwise, I think we'll keep going here. I think I'll just keep showing you more examples. So let's go back to the slides. I think I've got some more regression output to show you. So we go down here. Okay. So I had another data set, and I'll actually pull the Excel file up here in a second because I have it. And it was from this large survey, and it had the individual's income and the number of days kind of self-reported that they smoke or kind of use marijuana each month. So I had about 5,000 observations. These were younger individuals, and it was kind of started in 79. So this is kind of older data. So the income is a little bit low, but I didn't adjust it for inflation or anything. And if we look at kind of the median for the kind of numbers of days used, it's 0. But we have a lot of individuals kind of on either side of that mean. Right? So another way that I might be showing you regression output is not in Excel, but using something, another statistical program called Stata. You don't have to worry about this if statement here, but basically what I did is I just told it the Y variable is income, and this X variable is the number of days someone uses marijuana each month. Okay. So I run that regression, and it spits out at me these coefficients. So in some programs, like Excel lists it as the intercept. Other programs might call that the constant, right? Those two things are kind of interchangeable. That value A, the intercept, is also sometimes called the constant. Okay? So if I'm trying to interpret these here, how would I interpret kind of, well, first of all, how would I interpret the constant? That one's kind of easy. We said the general form is, of the interpretation intercept is, it's the predicted Y value when our X variable is equal to 0. So when someone uses marijuana 0 days a month, their predicted income is $32,000 based off of this sample data. Like I said, these were younger individuals, so we probably don't want to use this to like make statements about the population. But that would be the interpretation. Then the interpretation of our kind of coefficient on our X variable, the number of days someone uses marijuana each month, will be that for every additional day you use marijuana in a month, you could expect somebody's predicted income to go down by $253. And the p-value is pretty much 0, so we could say this is statistically significant at the whatever level, right? 1, 5, or 10% level, or that it's different from 0. So that's how, this is another example of how we would do interpretations. I think, do I have that here? Yeah, so I have it kind of typed out here, right? How would we, interpret that 1 unit increase? Will be 1 more day, in this case, a month, right? Because that was our units. And then kind of our intercept value A, or that constant, I kind of already said in words what that would be as well. So you've got those kind of written out for you in the slide. Oops, I'm going to go back to, I have this, I think it's up there under that linear regression folder. It's called Weed Wages. I didn't think about changing the name on it. But it lets me find the file quick. So once again, if we go to data and we go to data analysis, hit regression, my Y variable, I'm going to select to be income. Once again, control shift down arrow makes it kind of easy to select that. And my X variable is going to be the number of days they use marijuana each month. So notice some people reported using every day, so we've got some interesting things going on in the data. But we'll hit OK. We now get this regression output, and this is basically what I just showed you. I just was using something other than Excel. Okay, so I don't know, not too bad. I think it's pretty easy to run these regressions, and then it's just a matter of interpreting our coefficients and then determining whether or not they're statistically significant. Okay. Now I want to point something out, especially once you get to kind of, if you do take a stab at it or you are working on that 5th assignment after today, Excel assignment. Let's say I go here to regression, and when I select these, I don't select the labels. So I'll show you why I always select the labels. So we're just going to start and select just the data, right? Not that name of the variable. So I didn't select the labels, so I'll click off on that. Now, if I look here, the reason why I select the labels is because otherwise it just starts naming this X variable 1. It's easy to forget, okay, what was the X variable? It never tells me in my output what the Y variable was. So like, this is just kind of hard to, makes it a little bit tougher, especially if I'm having multiple regressions. And what we end up eventually seeing is I can actually include multiple variables on the right-hand side. If I don't select the labels, it just starts naming them X variable 1, 2, 3, 4, and 5, and then, it's just a mess, right? So kind of always selecting those labels when you're running that regression is probably, is best practice, so to speak. Okay. So, we could do the exact same tests that we were doing before, that this true population slope is less than, greater than, or not equal to a certain value. We're always going to use that assumed true value of 0. I've kind of already mentioned that. So really, for every single regression, we basically have a two-tailed test, right? We're assuming that true population slope is equal to 0. Okay. So yeah, we start out assuming that there is no relationship. We stack the deck against ourselves because we're trying to find evidence that there is a relationship, right? That's what we're testing for, that there's some relationship that's not equal to 0 between that X and Y variable. Like I said, I kind of already jumped the gun with this earlier, but I just thought it was easier to kind of mention all at once. So just as a kind of a reminder, I kind of went through this earlier as well, but how would I find the test statistic if instead I ran a regression where the Y variable is birth weight, and I believe that's measured in grams, and smoking is really just a 1 for whether or not the mother smoked, a 1 or a 0. So if the mother smoked while pregnant, it was a 1. If she didn't smoke while pregnant, it would be a 0. We're going to think about the interpretation in a second, but let's say I didn't give you the test statistics here. How do we find that test statistic? It's simply that coefficient divided by the standard error. So here, if I'm looking for the test statistic for smoking, about -213 divided by about 49, it's going to be right around 4, right? -4. So our coefficient is negative. So I'm guessing if we, actually plug this into our calculator, we'll get negative 4.36. And the reason why I was saying I know it's around negative 4, if I round pretty egregiously, 200 divided by 50, it's about 4. Right? So that's how I knew it was going to be in the ballpark of around negative 4 there. Whoops. How would I interpret kind of this smoking variable then? So this gets a little bit tricky, and we'll start looking at, these are sometimes called dummy or indicator variables. So if they're just ones or zeros. So if we're looking at this smoking variable, a 1 unit increase, like before, right, it was 1 more point in the SAT, 1 more day of using marijuana a month. Here, the only values we can see are 0 and 1. So a 1 unit increase would be going from not smoking while pregnant to smoking while pregnant, right? Going from that 0 to a 1 predicts that the birth weight goes down by, 213 grams, right? Remember our Y variable is birth weight. So a 1 unit increase in the X variable, going from not smoking while pregnant to smoking while pregnant, would predict that birth weights fall by 213 grams. Okay. And then here, the intercept is the predicted Y value when the X variable is equal to 0. Well, here, when is the X variable equal to 0? When someone's not smoking while pregnant. So for a mother not smoking while pregnant, the predicted birth weight would be about 3,427 grams. Okay. So just getting more practice with different examples, like going through these interpretations. I think here, I might have just have repeated slides. Let me see what I want to do here. I don't want to waste time on that solution. What do I want to do? We're going to do that next class. Let's go up here. Oh, where was that? So I already kind of showed you how we can think about these error terms. If we wanted to actually look at these solutions, we already had those earlier. So I could do this in Excel. I don't know. I sometimes think this is not worth it as much because it just causes a little more confusion than anything. But I do have a Excel file up there that kind of shows you that. Let's say maybe, what did I do here? What's my X variable? E, so I did height, and then I did weight, right? So I wanted to know what's the relationship maybe between height and weight, right? So my Y variable, I thought of as someone's weight. My X variable, someone's height. Right? Knowing how tall someone is, I can predict their weight, potentially. Now you can imagine an example like this. I'm going to have some big error terms, right? Because there's a lot of other factors that would influence weight here other than height, but that's what I'm going to use. So this was when we said we had these equations like right here. I can create separate columns for this. So I took the average X and the average Y, right? We know how to find means. That's pretty easy. So I just found the mean height and the mean weight. For that first person, I then, oh, come on. Just want to get in the cell. There we go. I took their height and I subtracted the average height, right? Or X minus the average X. Then for this person's weight, I took their weight and subtracted the average Y, right? Or the average weight. So now for this person, I have their difference, right? Whether or not they're above average height and above or below the average weight. I multiplied those two things by each other, right? If I then add up all of those products, right, for every single observation, the difference between the average X and the difference between the average Y, if I add all of those up, right, which is what I did here, that's my numerator. So that was basically just using Excel to calculate this numerator. I then would need to find the sum of X minus the average X squared. So what did I do over here? I took kind of the difference between X and the average X, and I squared it, right? I then did that for every observation, and then added them all up. That's my denominator. So to get my slope coefficient, I would divide that numerator by the denominator, and I get my slope coefficient of 4.7. Okay? Now, why would you do this? I don't know, because we've got that linear regression tool that will do all the work behind the scenes for us and just spit out us that slope coefficient. Okay, so you don't have to do this, but you could, and this is what you used to have to do by hand. Right? Before we had computing power and you wanted to run a regression, or come up with what a slope coefficient was, you had to go through this process. And not just this process in Excel, right? You had to do this by hand, manually calculate all of these observations. So you can imagine what limitations that would cause. Right? Now, just to kind of prove to you this works, let's actually just run a regression real quick where we look at my y variable is weight, and then my x variable is height, right? So I just select those. I selected the labels, 4.713. We go back up here where we had our calculation earlier, 4.713, right? We get the exact same thing. So, Excel will do all that work behind the scenes for us. So that's what we're going to, take advantage of that tool. And we're really going to spend kind of Friday and then kind of next week prior to reviewing for the exam, really just trying to get these interpretations down, think about things like making predictions. I'll introduce on Friday the next idea, which is that we don't just have to have one variable on the right-hand side. We can actually include several and think about how that changes the interpretation. It doesn't change it too much, don't worry. But we'll really just keep hitting more examples of stuff like this where we're running a regression in Excel or looking at some output from Excel or a different statistical program, interpreting coefficients, determining what levels they're significant at based off of the p-value. Remember how we calculate test statistics, just coefficient divided by standard error, and think about a couple of additional issues that will exist when we have multiple variables on the right-hand side. Okay. But this should give you a pretty good, at least kind of get a start on some of the Connect number 5 and then Excel. Probably after Friday would be easier to tackle the Excel because we're just going to be including more variables on the right-hand side. But you could probably get started on it and get a pretty good, good amount of it done. Okay. Any questions for me before we end today? Okay, I will likely put up. I will when I get back to my office put up a online quiz today. That'll be due before we start class on Friday. Other than that, I think that should cover it. So I will see you guys on Friday.